Exponential functions. Our objective is to evaluate exponential functions as well as identify and graph exponential functions. Who uses this? Scientists model populations with exponential functions. So let's look at what an exponential function is. So an exponential function has the form f of x equals a times b to the x, where a is not equal to 0, b is not equal to 1, and b must be greater than 0. So, most important piece, our exponential function. F of x equals a times b to the x. Notice how your variable now is your exponent. So let's practice. The function f of x equals 2 times 3 to the x models an insect population after x days. What will the population be on the 5th day? So we're going to substitute in 5 for x. So f of 5 equals 2 times 3 to the 5th. And when we simplify 3 to the 5th, we end up with 2 times 243, which then equates to 486. So on the 5th day, the insect population will be 486. So now let's look at this next one. The function f of x equals 1,500 times 0.995 to the x, where x is the time in years. This models a prairie dog population. How many prairie dogs will there be in 8 years? So we're going to substitute 8 in for our x value. So we have 1,500 times 0.995 to the 8th power. And we simply put this in our calculators. And when we do, we get it's about 1,441. So after 8 years, there will be about 1,441 prairie dogs based on this model. So recall back. When you dealt with a linear function, the first differences were the same. So that was when you added plus 3 plus 3 plus 3, or subtracted minus 2 minus 2 minus 2. If you wanted a quadratic function, the second differences were the same. So you checked your first differences, and then when you did the second differences, you ended up with like plus 2 plus 2 plus 2. And that would have been quadratic. However, you have an exponential function if it's a common ratio, meaning you're multiplying. So from 6 to 18, it was times 3. From 18 to 54, it was times 3. And from 54 to 162, it was times 3. So because you keep multiplying, you have a common or consistent ratio, it makes it exponential. So let's practice. So we want to look at our y values, because as long as our x values are increasing by the same amount each time, so -1 to 0, 0 to 1, 1 to 2, so we're good to go there. So now we're going to look at our y values. How are they changing? So to go from 1.5 to 3, we're going to be multiplying by 2. From 3 to 6, we're multiplying by 2. From 6 to 12, we're multiplying by 2. So we keep multiplying by the same ratio. It's consistent. So, since we're multiplying by a consistent amount, it's exponential. Now let's look at b. So to go from -9 to 9, because we're just looking at our y values here, we ended up multiplying by -1. Then to go from 9 to 27, we're multiplying by 3. And now we're going from 27 to 45. Well, this gets weirder. We're multiplying by 5/3. Well, we're not multiplying by a consistent ratio, or a consistent amount, so therefore it's not exponential. So now let's look at graphing. So we're going to try to graph y equals 3 times 4 to the x. So you're going to pick a few values for x and substitute them in. I suggest keeping numbers that are pretty small. So we've got -1, 0, 1, and 2. So we're going to substitute the -1 in for x. So we have 3 times 4 to the -1. So 4 to the -1, if you recall, is the same as saying 1 over 4. Let me write that. So we're going to go down below here. So if we substitute a -1 in, this is the same as saying 3 times 1 over 4. Because when something's to a negative exponent, we need to move it downstairs. So now we have 3 times 1/4, which in the end gives us 0.75, or 3/4. Now let's substitute in a 0. Well, anything to the 0 power is simply 1. So 4 to the 0 power is 1, and 3 times 1 is 3. Let's keep going. So 4 to the first power, we're substituting a 1 in for x, so 4 to the first power is 4, and then 4 times 3 is 12. And now we do the same thing with the 2. We substitute the 2 in for x. So 4 to the second power is 16 times 3 is 48. Once you have your x and y values, you can plot them. So when you plot them, you go across your x, and that's your -1, and we went up 0.75. Then we had 0, 3, 1, 12, and 2, 48. Notice how the graph increases rapidly as it goes off into infinity. Positive number and a number greater than 1. Let's see if you can notice a pattern that ends up happening as we continue. So let's do the same thing here. Only this time we have a negative a value. We have -5 times 2 to the x. So we're going to substitute each of these values in and get our table of values. So take a moment and pause the video. When you return to the video, the answer for the table will be revealed. So now that you have your table of values, you have your x and y values, we can plot those. And when we do, we end up with -1, -2.5, 0, -5, 1, -10, and 2, -20. And notice how the a value is negative, and it shows a decay. It's dropping off. It's decreasing rapidly. So when it's positive, so when your a value is positive, it shoots up from left to right. When it's negative, it shoots down from left to right. Well, now what happens when this b value is less than 1? So take a moment and fill in your table of values. When you return, the values will be revealed. So now that you have your table of values, we can plot those points, just like we've been doing. So we had our -1, 6, 0, 3, 1, 1.5, and 2, 0.75. Notice how when your b value is greater than 0, but it's less than 1, so when this is a fraction, if you will, it shoots from right to left and goes up. So we're going to go off in the backwards direction, but we're still going up because the a value is positive. So we're still going up because the a value is positive. We're just going in the other direction since we have this fractional piece. So let's recap here. So when we have a positive a value and a number greater than 1 for b, we go left to right and it shoots off into infinity. When we have a negative a value, it still goes left to right, but it drops substantially. So it goes in a negative direction. And now, when our b value is less than 1, but our a value is positive, it still goes up, but it goes up from right to left. So make a hypothesis about a negative a value with a fraction or decimal. Which direction is the graph going to go? Is it going to go from right to left? Left to right? Is it going to go up or is it going to come down? Take a moment and complete the table of values. When you return to the video, the answer for the table of values will be revealed. Once you have your table of values, we plot our points. So, when we have a negative a value, we go down, whether it's down to the right or down to the left, but because we have a fraction, we go down towards the left. This is a summary of everything we just did. So, for y equals a times b to the x, if b is greater than 1, then the graph will have one of these shapes. So if b is greater than 1, it's going to go from right to left, from left to right, and if your a value is greater than 0, going from left to right, it's going to shoot up. If it's less than 0, going from left to right, it's going to come down. If the b value is less than 1 but greater than 0, we're going to go right to left. So if it's a positive a value, we go up. If it's a negative a value, we go down. So now let's look at a statistics application. In the year 2000, the world population was about 6 billion, and it was growing by 1.21% each year. At this growth rate, the function f of x equals 6 times 1.0121 to the x gives the population in billions x years after 2000. So we're going to use this model, and then in about what year will the population reach 7 billion? Notice how we're talking about everything in billions. So 6 billion in billions, 7 billion, and we just wrote a 6 here. So we're just going to take it as though it's a 6 instead of 6 billion when we're trying to put the function into our calculator. But keep in mind that 6 represents 6 billion. So you're going to hit your y equals button on your calculator, and then under y1, you're going to type in your 6 times 1.0121 to the x power, because that's what we're actually trying to find. We want to know what this x value is when our y value is about 7 billion. So we're going to use our table of values. So once you enter this in, you're going to hit second and then graph. This will give you your table. You'll have an x, y table. So you're going to look down your y values and find how long you go down, and look for one that's really close to about 7. And then what were the years? So because x is time, so x is years after 2000, and we want to get to 7 billion. Well, it was about 13 years, because that's when you ended up with 7.0155. So that was about as close as you were going to get to 7, and it was 13 years. So in the year 2013, the population will reach 7 billion. That concludes our lesson on exponential functions.